In this presentation, we'll continue to talk about the transfer of energy via heat. And it turns out that there are three mechanisms for heat transfer: conduction, convection, and radiation. And we'll start with the first one, which is conduction. In conduction, the transfer of thermal energy is by direct contact between two objects that are at different temperatures. This is probably the one that we're most familiar with. One easy example is if you take a metal spoon and you leave it in a pot of soup on the stove, and you go over and you go to grab the end of the spoon, it'll get hot. And it'll be hot on the end. And that's because energy was actually transferred from one end of the spoon that was in the pot of the soup to the other end that was sticking out in air. You could take the same situation, except put a wooden spoon in the soup, and you go over, a couple minutes later, and the end of the wooden spoon is not hot. So there's obviously a difference between how energy was transferred between the metal spoon and the wooden spoon because of the fact that the ends of those two objects were at different temperatures. One in the hot soup, the other one in the air. So conduction is actually occurring sort of at the atomic level. And so if you look at this picture, so we have a fire right here, we have the hand over here. So this is sort of the same example that we just talked about with the wooden spoon versus the metal spoon, except in this case it's a glass rod and a metal rod. And so what's happening here is one end of the rod is placed in the fire, and then the hand is holding the other rod. The same thing with the metal over here. And so what's happening is that the molecules inside of the metal, for example, so here's the metal to start with, they get warm on one side, and there's a lot of free electrons in the metal, and so that energy is transferred to the molecules that are next to it, and that continues until it gets to the hand. So the fact that there's these free electrons inside the metal actually allow that energy of the molecules that are getting excited from the heat and the temperature increase to pass that along to the molecules that are next to them, and then eventually it gets to the hand. On the other hand, the piece of glass does not have those free electrons, and so although the molecules do get excited and they start to vibrate a little bit, it's harder for them to transfer that energy to their neighbors. So different materials will transfer energy at different rates. But the thing about conduction is the energy is transferred from it's transferred through the material, and it's due to a temperature difference. So one end of the metal is at a higher temperature than the other end of the metal, and so energy is transferred from the warmer end to the cooler end. And it's the same thing with the glass rod, it's just not transferred as well. So we could talk about conductors versus insulators, and something that is a good thermal conductor allows energy to flow via conduction very quickly, very easily. So it's going to have a large rate of heat flow, and of course heat is energy, in a small amount of time, right? So metals are very good conductors of electricity, and they're also very good conductors of heat. And the reason that they're good conductors of electricity and good conductors of heat is for the same reason, and that's because they have these free electrons inside the material that are not tightly bound to the molecules, and those electrons can pass that energy on very easily to their neighboring molecules. An insulator is something that is slower to transfer energy via conduction. So the rate at which the energy flows is smaller. Some good examples of that are wood, plastic. Air is actually not a particularly good conductor of heat, so it's considered an insulator. Carpets and things like that. So any substance that can trap air inside of it is actually a good insulator. So some others are fur, feathers, and actually snow is a good insulator. Now snow is cold, but if you were to build like an igloo type thing and then you get inside, it actually would be pretty good at keeping the heat inside from your body versus allowing that heat out to the outside of the igloo. So good conductors of electricity are also good insulators because of the free electrons, and insulators are not very good at conducting electricity or conducting heat. or energy, and also they have very few free electrons. So we could ask the question, what property could have an impact on the amount of heat that's actually transferred through the material? And so one thing that has an impact is what the thickness of that material is. So the greater the thickness, the less heat that's transferred. So if you're wearing a bulky coat, that is going to keep you warmer in general, because it's not going to allow the heat transfer from your body to leave your body and go to the outside, which would be colder. Another example is home insulation. So the thicker the insulation is, the better it is at insulating the house and not allowing the heat transfer from the inside of the house to the outside of the house in the wintertime when you want to keep your house warm. And also it's the opposite. So on a warm day outside, you don't want the heat to transfer into your house where you're using your air conditioning. So in general, if you have a given material, the thicker that material is, the better it's going to be at insulating and the less heat that's going to be transferred. So thicker material, less heat transfer. It's also going to depend on the temperature difference. So the bigger the temperature difference is between the two sides of the object, the more the heat that's going to be transferred. So if it's really warm outside, then you could imagine, and you had ice that was located, let's say, in a cooler. It's not a great cooler, but it's in a cooler. The ice is going to melt faster if it's warmer outside. So, so the bigger the temperature difference. If there's no temperature difference at all, then there's no heat transfer. So if you had the house with the insulation, if the temperature outside is exactly the same as the temperature inside, there's no heat transfer between the inside of the house and the outside of the house. It also depends on the area of contact. So the larger the area of contact is, the more heat that's transferred. That should kind of make sense, because if you have a larger surface area, you've got more ways that the energy can go through that thickness of the material. So for example, if you have a larger cooler, and then you had a smaller cooler that had a smaller, that had the same thickness associated with it, the larger surface area cooler would actually transfer more heat from outside. So if you're trying to keep your drinks cold in a large cooler that has the same thickness as a smaller cooler, the energy is actually going to transfer more quickly into the larger cooler. Now, there's other things going on there. I'm assuming here that we just have a cooler. We're just putting like a 6-pack of soda in one cooler, 6-pack of soda in another cooler, and we have to think of things evenly in that way. But the larger area, the more heat that actually can be transferred. It also depends on the type of material, as we saw with the example of the glass and the metal. So conductors are going to transfer more heat. They have what's called a large conductivity, and insulators are going to transfer less heat. They have something called a small thermal conductivity. So the thermal conductivity is going to tell us what type of material I have and how well that it is going to transfer energy. So something with that high thermal conductivity is a good conductor of heat. It's going to allow that heat to go readily through it. So metals have very high thermal conductivities. Low thermal conductivity is a good insulator. It's not going to allow the heat to transfer very readily, and so glass actually has a low thermal conductivity. So here's a table of some different thermal conductivities just to give us an idea. At the top here are some metals. So for example, copper has a thermal conductivity of 397. Aluminum has a thermal conductivity of 238. Copper is a better conductor of heat versus aluminum. So if you took a piece of aluminum and a piece of copper and you stuck them both into a pot of warm water, and they were identical in every way except one was made of aluminum and one was made of copper, the copper would actually have a higher temperature at the end quicker than the aluminum because it conducts heat better. We have some nonmetals down here. Here's glass. Glass is actually a pretty good insulator. If I compare its thermal conductivity, it's very low thermal conductivity compared to the values for the metals. Ice is actually a pretty good insulator. And then we've got some other ones as well, wood, and then we've got some gases. Gases are really not very good at conducting energy via conduction because of the fact that the molecules are so far apart. And so they transfer that energy through the material because the atoms, molecules get excited when the temperature increases, pass it along to the next one, but in a gas, the molecules are much further spread apart, so it's harder to transfer that energy. Another method of heat transfer is called convection, and convection occurs when there is a bulk movement of a fluid. And so here's a picture that's sort of showing an example of that. It's just going to keep repeating, but it's just a container of water. There's some dye at the bottom, and it's really hard to see, but it's sitting on under a flame. And as that fluid temperature increases here, the fluid movement is in the upward direction. And so what's happening is there's transfer of the heat from the bottom moving up into this container because of the bulk movement of that particular fluid. These are called convection currents. So in convection, when the energy is transferred from the bulk movement of the fluid, the way that it's transferred is by currents, and these are called convection currents. And so what happens in general is that warm fluid on the bottom moves up, and it's replaced by the cooler fluid. So when this goes up, cooler fluid replaces it, that heats up, and then that process just continues to repeat itself. So here's some other pictures. These are just some hot cups of probably coffee or something like that, and then there's a fluid in here that has some dye. And if you've ever seen a lava lamp, it's the same process as well. So the bottom of the lamp has a light or something on it that produces heat. When it gets hot, the bubbles go up to the top. When they cool, they fall back down, and then that process continues. But this is transfer of heat via convection. So why is it that the warm fluids actually do rise from convection? And what happens is as the fluid's temperature increases, it expands, right? So the fluid that's at the bottom of that container that was heated up, as the temperature gets up, that fluid expands, and as it expands, its volume increases. And as the volume increases, the density actually decreases. So density is mass per unit volume. So warm fluid becomes less dense because the volume of that fluid has increased, the mass has stayed the same, so it has become less dense. So warmer fluids are less dense than cooler fluids. And then, of course, we know that less dense fluid is buoyed up. So according to buoyancy, something that's less dense is going to float compared to something that's more dense. So when you have these two fluids, or when we have this fluid, this water, let's say, and the bottom becomes warm, it becomes less dense than the cooler water above it, so it floats up above, the cool water sinks, and then that process basically continues. Right? So that repeats that rise and that fall of the rise of the warm fluid, and then the fall of the cooler fluid continues. So in convection, you basically are just having the bulk movement of a fluid, and the reason that fluid moves from one place to another is because its temperature increases, it becomes less dense, the fluid rises, is replaced by the cooler fluid. Convection currents are also a process that occurs when you're near lakes and ponds, and so this is just a little picture of how you can get these convection currents. So on a very warm day, if you're near the ocean water might be cooler than the temperature, outside. So the water or the air right above the ocean is cooler than the air right above the land where it's really hot. And so what happens is that warm air near the land rises up, and then it's replaced by some of the cool air from the ocean. So if you go to the ocean, you'll notice on a really hot day that sometimes you'll get those nice breezes that will come in from the ocean, and that's because of these convection currents. And you can actually have the opposite occur at night. If it cools down quite a lot, you can actually have the cooler air go out towards the ocean and then rise up. So this process can actually be in the opposite direction if it is nighttime. The last process of heat transfer is radiation, and radiation is different than convection and conduction. So with conduction and convection, you need a medium to travel through. For radiation, you do not need a medium to travel through. It can be transferred across the vacuum of space, and so the thing that should come in mind sort of is like electromagnetic radiation, if you've heard that term before. So in the process of radiation, energy is transferred via electromagnetic waves. So for example, energy from the sun can cross the vacuum of space and it reaches the earth. And so there does not have to be any sort of medium at all for that heat to be transferred. So some different examples of radiation is if you have a little heater in your house on a cold winter day and you're sitting in your chair, that energy is radiated outward from that heater via conduction. Of course, we've got thermal energy from the sun from radiation. If you're sitting next to a campfire, your hands can get warm if you place them to the side of the campfire. So, you've got some radiation occurring here. There's other ways you can transfer energy when you're looking at a campfire. So if I think about the campfire example, certainly the air above the campfire is being warmed and it rises, and you can think about the smoke that occurs there. That's the transfer of energy due to convection. So you've got convection currents that occur on the campfire going this way. When you're alongside the campfire, that's the radiation. The energy is actually radiating out in all directions. And then the last example with convection with the campfire is if you were to roast a marshmallow over your campfire and you were to put one of those metal roasting sticks in there, the energy would be transferred through that metal stick, and that's conduction. So if you've ever done some campfires, the end that you hold on to is usually made of wood and not metal, so that that energy is not going to transfer to your hand as easily. So it turns out with radiant energy, any object that has temperature actually radiates energy. So, as we are, just standing and our bodies have temperature associated with it, we radiate energy. And so if you think about getting under the covers at night, right, you kind of get nice and warm. Well, part of the reason that you get nice and warm is because your body is radiating energy, but your covers are keeping you insulated from letting that energy escape out into the room. So you get nice and warm, you stay nice and warm. So it turns out that objects can radiate and they can also absorb energy, and it's based on the temperature of the objects and based on the temperature of the surroundings. So when we think about this in terms of absolute temperature, we have to think about Kelvin temperature range. So something that's 0 Kelvin is at absolute zero, and it would not radiate any energy at all, right? Because it's at 0 Kelvin. But any other temperature, an object can radiate energy, but at the same time, it can absorb energy as well. Thermal equilibrium is reached when an object radiates and absorbs energy at exactly the same rate. So if an object is at a constant temperature, that means it's in thermal equilibrium, and that means that it is both radiating energy and absorbing energy. So an example would be that suppose that we leave a container of water outside on a warm day. So the water will heat up due to the absorption of the electromagnetic waves from the sun. But eventually the water will get to a certain equilibrium temperature. So we leave it out there, the water gets nice and warm, eventually it reaches a particular temperature. At that particular point, when the water reaches an equilibrium temperature, the water is absorbing energy from the sun, but it's also radiating energy at exactly the same time. And the rate of absorption from the sun energy is exactly equal to the radiant energy that is being emitted from that warm water because it has temperature associated with it. So when we're standing in a room, our bodies are radiating energy, but we're also absorbing energy from the room as well. So every single object that has some temperature associated with it both emits and absorbs radiation. If it emits, if it gives off, if it radiates more than it absorbs, then the temperature is going to decrease. So basically it's giving away more energy than it's taking in, and so the temperature of that object is going to go down. On the other hand, if it absorbs, if it takes in more than it emits, then it's going to increase. So it's gaining energy more than it's losing energy, and so its temperature is going to go up. And if it emits the same amount as it absorbs, then the temperature is going to remain the same, right? So that process of taking in and giving away, it's staying the same value, so that temperature is going to remain exactly the same. So we can have an idea of when the temperature increases, decreases, increases, or remains the same in terms of radiation, what's actually going on. So suppose that I have a cold soft drink that's sitting on a counter and its temperature is increasing. How does the rate of absorption compare to the rate of emission? All right, I'm going to go ahead and put this in here. There we go. And I'm just going to talk through it because for some reason it was going on its own. So I have this cold soft drink and it's sitting here. Its temperature is increasing. How does the rate of absorption compare to the rate of emission? Since the temperature is going up, the can absorbs more energy than it radiates or emits, right? Eventually, the soft drink reaches a constant temperature. So it's sitting in the room. Maybe you pulled it out of the refrigerator. Maybe you pulled it out of the refrigerator and it was cold, right? And then the temperature increased because it was sitting at room temperature. So eventually it reaches a constant temperature. How does the rate of absorption compare to the rate of emission? Eventually, when it reaches a constant temperature, the can absorbs the same amount of energy that it radiates, right? So it's not taking in any more than it's giving away. So because of the fact that a system can reach thermal equilibrium, that means that anything that's good at emitting radiation is also very good at absorbing it. Because if it eventually reaches equilibrium, and it was really good at radiating, but it reached equilibrium, then it had to also be very good at absorbing. And the same thing is true if it's a poor emitter of radiation, it's also a poor absorber of radiation. So I just wanted to sort of show sort of a summary picture of this example with the boiling water. So you've got a pot and it's on a burner, and this shows all of the possible types of heat transfer. So there's conduction due to the fact that there's contact of the hot plate with the bottom of the pan, and so there is energy transferred from the higher temperature hot plate part into the pan. And then there's convection because the molecules of water get warmer, so the water warms, it becomes less dense, it rises to the top, so you've got the convection current. And then if the pan is really warm and you put your hand over here, there's actually energy transfer due to radiation because it's at some temperature. So all three of these are possible when you think about just water boiling. And it's the same thing example as the campfire example before.